Hello, everyone. This is lecture 12 of PTRE 475575. Today, we will, if there is any questions on the homework, I will go over them. If there is, other than that, the homework two is due on Thursday, 1 minute before midnight. Homework 2 is much easier than homework 1, although homework 1, which has been graded, and we should all be thankful to the TA because he came back from Houston on Friday evening or Friday afternoon. He graded the homeworks over the weekend and was ready to give 2 laboratory sessions yesterday. And I couldn't be there because I was with a delegation that was meeting with the SP president who was visiting our department. She's actually here right now. She's touring either ERC now or the core library. The grades for homework 1 were not bad, but they could be improved. There was 100, 98, 95, 80, 72, 60, 50, and 80. I would say the 60, 50, 60, 72 should be improved. 80 is more or less okay, but it's good if it goes higher, and the rest are very good. Now, admittedly, homework 1 was hard, okay? And I have to give congratulations to those of you who got excellent grade in homework 1. You actually did an exercise that a lady did in mid-2000s in Australia to constrain the SH max, local SH max at what is known, I think, the West Tuna area of the Gippsland Basin. So what I gave you is an actual real-world problem. So congratulations to those of you who got it right, and it wasn't easy, and you did very well. So yeah, I don't know if I'm gonna need 2 lectures for review, but last year I did 2 short lectures for review ahead of the exam. But this year, I mean, I don't want to fall behind, so I think of carrying on a little bit into module 2 on stuff that are not gonna be on the exam. And then maybe if we have the time today, but certainly on Thursday, questions on the exam, because next Tuesday, 1 week from today, is the exam. Okay. Another thing I wanted you to know is that the rules changed a little bit with PTRE. And you know, PTRE, we paid a lot of money to PTRE to handle our exams, our online exams. And it's a separate entity, and some things are out of our hand. If you book an appointment and you change it late, like the last days of the exam, the last like within, I don't know if it's 48 hours or something, there is a fee, but it's I think $100 or something. Don't quote me on that, but anyway, so Miss Corday told me so that to warn you, like, don't get into a situation where you have to change it last minute because they are trying to bang on you in the sense of, like, I think they see it as an easy way to make money out of, well, students, which is ridiculous if you ask me, but anyway. So yeah, be organized, make sure you have all the components that you need, which I don't know myself, and do the exam. we are not involved unless you guys get caught cheating or something. If you get caught cheating or something, or they generate a report and they send it to us along with the video, and generally it doesn't come to me. It goes first to the ladies downstairs who handle the online system. And if it becomes subjective, it comes to me. 1 year they caught somebody during the final, the first semester I was teaching here. They caught him going off the window that was the exam, trying to Google the answer to a question. I mean, it was pretty slam dunk. I couldn't do much about it. Another time, they caught somebody having somebody else take the exam for them. And this person, they raised a concern because it was raised a concern about that person because he was enrolled into weird combinations of classes, like he was taking a class in petroleum, a class in biomedical or something. It didn't make sense, the courses that they were taking. And big congratulations and thank you to the ladies downstairs because they noticed that from the video, it was really not the same person that was taking the exam. And they put it together. And I think one of our associate deans was very, very adamant that we need to expel the student. I don't know what happened, but well, he was dropped out of the class, possibly, and I don't know what happened of him. This is a story that is like 2.5 years ago. So it was a long time ago. I'm just saying, there was another case. A student was caught trying to write in his hand. He was trying to do like a calculation or something in his hand, or like some derivation, and this was touch and go. So it came to me, and I thought it. I was like, it makes sense. Don't bother him about it. But then I took extra action to allow you now to use a scratch paper that you have to destroy after the exam is over. So I learned from that too. And that was my first semester teaching. So the way it is, I think you are allowed a calculator, scratch paper, a ruler. You may not need a ruler, but you're allowed to have. And the exam is 75 minutes. And I will say this to give you, it's really designed for 50 minutes. And I'm giving you 75 minutes. So, or like designed for an hour, and I'm giving you 75 minutes. The hour includes also going over reviewing. So don't rush too much. Just when you take the exam, find the easiest question, start from that. It may not be number one. Okay, it may not be number one, the easiest question, but start from the easy question, then move to the second easiest, third easiest. So you build confidence. And then you basically attack the hardest problems at the very end. So you are confident and you're like, okay, I'm gonna try to get as many points as you can. Think about it. You're trying to get as many points as you can. You don't want to leave behind easy points because even if it's a hard exam, it's hard for everyone. So if you write the highest grade, if the highest grade of the exam is 50, and 50 sounds like a bad grade, it may not be a bad grade. So make sure you get that 50, or you get as close to it as possible. What I tell my own students is that, my graduate students, is that make sure that this number that you receive is the highest you can possibly get. It's just like when you go to a race, and if the best you can do is the 7th place, make sure you get that 7th place. You know, don't be very mature in your approach, I would say. Anyway, not about the exam, which we're going to talk about it next Thursday. We will review, and then Tuesday you come back and it's the exam. You will have at least 1 second. Um, what I was gonna say, it's you will have at least the solution key for homework 2 before you take the exam, no matter what. So yeah, even if we don't manage to grade it on time before you take the exam, you will know the answers. Okay, and homework 2 is pretty straightforward, but important. But important. All right. So we said for the exam, it's gonna be up to slide 20, which is where we ended up last time. And yeah, now we'll carry on today a little bit further. I want to get close to as much as possible before I start reviewing. If we have extra time today, I don't know. This is long lectures. I might start the review for today to save time. Since I know more or less what is gonna be in the exam. So packers, this is something that is more production engineering than completion engineering, but we have to go through that because there is overlaps. Okay, packers are part of the completion system. They assist production. Okay, and the good thing is that many of you have seen this stuff in 421 or a version of this stuff. So it's good for moving forward. So we have production casing or liner, and then inside it we have a tubing. And the tubing is production tubing. And the tubing is held in place with a set of packers that they provide hydraulic isolation between that tubing and the casing. There are several types. Many of them they have expandable components that they help seal on the wellbore. So you start with a small OD and then you expand and it seals around the wellbore. They employ flexible elastomeric elements that expand. There is a lot of technology going on into packers, okay? And a lot of technology related to hydraulic fracturing that go into packers because they do play a role. And also when it comes to injection and when it comes to injection and, carbon sequestration, this wastewater disposal, anything that you have that pressurizes the wellbore, you prefer to do it via tubing so that the casing is safe, is under low pressure. If the casing is under low pressure, the cement shed would be under low pressure, and the rock around it would be under low pressure. So you basically are protecting the well integrity. So in this case, for instance, you want, where is the pen? Only the fluid inside here to be high pressure, not the fluid here. And therefore the cement is safe. And so there is a lot of technology going on, but there is so much you can do, the tubing has its own rating, okay? You don't want to over pressurize the tubing, then you're going to have other kinds of problems. So, but a lot of technology in the service sector going on about packers. A downhole device used in almost every well completion to isolate the annulus from the production conduit, enabling controlled production, injection, or treatment. A typical packer assembly is used as means of securing against the casing liner wall, such as a slip arrangement, creating a reliable hydraulic seal to isolate the annulus. So hydraulic isolation is basically what we are targeting. Packers are classified by application, setting, installation method, and possible retrievability. Main types of packers, two of them, main categories: retrievable, packer body, slips, and rubber elements rigidly attached to the tubing string, can be weight set, tension set, or hydraulically set, can become unseated or move around. Permanent packers, sealing elements on tubing, set via wireline. WL is a common abbreviation for wireline. You will see it later in this module in particular, but yeah, and generally permanent, they have higher pressure rating than retrievable. And retrievable are the ones that are like, you may have a lot of problems, but it may be easier to fix them than with permanent. Now, tubing motion, these small boxes here are called packers, the packers. Let me use a different color. So hard to. Anyway, they hold the tubing together inside the casing. It's all about tubing in a casing. Now, the packer can move in several ways. They can move like up or down, piston-like movement, buckling, which can be very bad, very bad. Buckling it's a very common problem when it comes to tubing. Anytime we set the tubing in tension, under tension, intentionally, to make sure that it will take a safeguard against compression, you know. Ballooning is very common. Temperature effects are impacting the piston. They can make it shorter, longer, etc., etc. If you try to make it longer, if it heats up and it's metallic, it's gonna obviously heat up easily and attempt to become longer. And if it's restrained there, it's very likely that it's gonna lead to either ballooning or buckling. And the opposite, if it gets colder, it's gonna try to become shorter. So it's gonna move upwards like a piston. So it's a three-dimensional motion range that you can get impacted with packers. So we are gonna do basically a summation of all the forces acting on the packer. You have the force from above, fluid above it, fluid below it, and there is a difference between the two, actually, that's very important. Ballooning force, buckling force, and temperature. So force above, force below, ballooning, buckling, and temperature. Induced axial movement by the tubing, delta L, the measured depth of the packer divided by the cross-sectional area of the tubing times the Young modulus of the tubing times sigma F, the summation of the forces. And by that is basically the summation of the forces in the up and down direction, like the y-axis, let's say, or the z-axis along the wellbore. So this is what is influencing the delta L, the way you are gonna move up or down, okay? Now I'm going through this a little bit fast, and it might be confusing. There is two reasons for that. One is that you have already seen this stuff on a certain version, and two is that they may not, there may not be a lot of weight on that in terms of the grading in this class. Like I don't think I wouldn't worry too much about it when the exams come. Let's put it this way. It doesn't mean don't worry at all about it, but we will talk when that will be exam two. We have time after spring break, well after spring break. Any questions? Okay. Forces acting on packet tubing systems. Tubing movement allows or occurs or forces are induced when changes are made to the well. Running the packer. Oh, 1 second. Let me give the key to your PA. Let's see and correctly. Right. Because Telroki, they were emailing me from Dracula and from the code right now. And I forwarded to you. I will get it from you tomorrow. Let's meet text. Sorry, I had to give the drilling simulator key to the TA because he's taking the president for a tour there and they didn't know that they would need it. So he had to come over to get it. So when you are running the packer, you can cause movement, obviously. When you are placing the well on production, you can also induce movement. When you are swabbing, in this case, swabbing means taking a sample of the fluid. So you are swabbing. You can cause motion. You can trigger motion. Acidizing, fracturing, obviously. After the packer is set, each subsequent operation must be evaluated against the original setting installation conditions. Okay? Many times you may have a packer there in the packer tubing arrangement, and you may change something that goes on in the well. Okay, you may change it from producing at this rate. You may change the pump, so you are producing faster or slower. You may cause the packer to unseat. It's one of those weak links. Like it's like you may need to ask yourself, will my packer hold? Yes or no? Maybe. Exceeding the original setting forces may cause the retrievable packer to move or unseat. Sealing sub to slide out of permanent packer. Again, packer unseating based. Very, very common problem. Not so much these days. The companies have been good in making good, solid, robust packers, but they are still, it's not uncommon. Forces acting on the packer body, pressure changes in the tubing or the annulus will result in forces being applied to the packer body. Pressure is the same at the packer, but the dimensions of the top and the bottom of the packer are different. And this sounds weird. I'm gonna make a drawing that is gonna make it much, much simpler. Oh, yeah, I left that space to remember to do the drawing because it's important. The first time I was teaching this class, I flew past this. Oh my God, the students didn't understand what I was talking about. It was my mistake, actually. Then I realized, oh, I should have explained this better. So I have a way. It has uh, casing. And I know there is cement and everything, but I'm just casing. And then I have tubing arrangement. The tubing is yellow. And it goes up to here. Now I have a pipe here. Before I do that, the tubing also has walls. And the packer is set here. And now I hope I drew it well so that you can understand that if I have a fluid on top of the packer, let's make it turquoise, light blue. The area is acting on, cross-sectional wise, it's basically the packer, okay? This is the area it's acting on. Between the outer diameter and the inner diameter of the packer, like all this sort of donut-like shape, only perfect. Now at the bottom, if I have a fluid at the bottom of the packer, let's make it pink, it's acting not just along the packer length, but also the edge of the tubing. So at the bottom, let's see, this is the packer. Let me make it again. It's oh, okay, this is my packer. Okay, light blue is acting like this. But inside the packer, I have yellow, and I have yellow here, and then another yellow. And inside the yellow is the tubing. Now, pink is acting all this direction. So the length of the pink is like longer because it includes also the walls of the tubing. Remember, stress is pressure times cross-sectional area. In this case, the cross-sectional area is bigger. So bigger area at the bottom than the top. And this can be quite important. We're going to see an example later on in this module, like in a few slides, that will make you understand that there is quite an imbalance there. If you are, especially if you are using fluids of similar density, and you need to take account of this difference. It's quite important. Forces on the seals of the tubing in place. F above is calculated considering the tubing's slacked off weight, FSO, weight of the tubing while entering the hole. That's like an industry term, slacked off weight. It's like takes account of the friction with the fluid, basically, as it's entering the hole. Think about it similar to what we were saying in drilling search. F above equals to FSO plus pressure on the surface in the annulus plus TVD of the packer, the true vertical depth of the packer, times the gradient of the fluid in the annulus times the cross-sectional area of that blue that we were mentioning above, the light blue, which is pi OD of the packer minus the OD of the tubing, both of them squared divided by 4. And assume that the OD of the tubing is basically equal to the ID of the packer. Same thing. I expect where the packer ends, the tubing begins. Force below is negative, acting upwards, minus P surface on the tubing side, plus TVD of the packer times the pressure on the tubing is like whatever I have inside the yellow tube, which I didn't draw anything in this, because I'm assuming that that pink fluid I drew earlier goes into the tube as well, right? Times the pressure gradient of that fluid times pi OD of the packer minus ID of the tubing. Okay, now that's the pink arrow I drew earlier, which is longer. Okay, ID tubing square OD packer square divided by 4. If the tubing cannot move, the force on top, F top as we call it, is calculated using the tubing's Boyd weight, WB, tube, Boyd weight. So again, it takes into account being immersed fully into a fluid. Like slack of weight is moving into a fluid. Boyd weight it involves basically Archimedes principle, the fluid that you are displacing. F top equals MD packer W times WB tubing minus F ballooning minus F temperature minus FSO. Okay, that's the force on the top of the packer. Force, okay, not pressure. It's pressure times cross-sectional area, basically. And then let me clean up. Temperature change induced force, F temperature. If there is temperature changes, they will be given by A tubing, the cross-sectional area of the tubing, times the Young modulus of the tubing, whatever the tubing is made of, steel or whatever, times the linear thermal coefficient alpha T times delta T, the change in temperature. I'm giving you here some values for steel, linear thermal expansion coefficient, I forgot, and then alpha T. Ballooning induced force, F ballooning. Now this is a weird equation, but take it for what it is. You can derive it if you want, but it's beyond the scope, beyond the chapter of this course. I mean, this is a conditions course. I want you to know it though. 0.15 pi times the change in pressure in the annulus times the OD of the tubing square minus the pressure change in the tubing times I internal diameter of tubing square. Any questions so far? It's pretty straightforward. Okay. Backlink force calculation. This is a little bit more complicated to do analytically. So there is some empirical components in the expressions that we are seeing for this stuff. For permanent backlink, the backlink force is given by cross-sectional area of the packer, from the outer diameter of the packer to the inner diameter of the packer, or the outer diameter of the tubing the packer has sealed well, times the change in pressure in the annulus minus the change of pressure in the tubing. Change of pressure in the annulus is given by the change of pressure on the annulus at the surface plus TVD packer, the depth of the packer times the change in pressure in the annulus divided by 2. Same thing for the delta P of the tubing, the pressure on the surface, the change of pressure on the surface, plus TVD Parker times the gradient of the fluid pressure gradient in the tubing divided by 2. Hence, we have this equation for the buckling, which is not the nicest equation I can come up with, but I guess it's good enough for what we needed for this class. And again, this is not a production class. Don't want to get too much into, I don't want to get into too much detail, because that's somebody else's job to teach you production. I'm just responsible, I guess, for the overlap. I don't want to make too much of a change. So, but let's use an example problem to make things clearer, which I believe they are going to be clearer after this one. A well is equipped with a weight set packer. The packer was set with 7,000 pound force of downward force, weight set at 6,500 feet. The pressure in the casing annulus acts on the top of the packer's cross section. Tubing pressure acts on the bottom of the packer cross section. When the packer was set, the tubing and annulus contained 9 pounds per gallon salt water. Now, this problem is basically what I drew earlier. Okay, it even tells you cross section of the top packer is 14.81 square inches. Cross section of the bottom of the packer, 16.11 square inches. Why is not the same? Because of what I mentioned earlier. The bottom includes the thickness of the tubing walls, which is not much, but it's enough to make a difference. I set it with 7,000 feet downward force, weight set. This is a fancy way of telling you I set it on tension. Okay, I set it at 7,000 pound feet, 7,000 pound force, of tension. For a packer set at 6,500 feet, this results in a hydrostatic pressure in the annulus of 0.052 times 9 times 6,500 feet. You should remember this equation, 0.052. If I'm given the density in pounds per gallon and the depth in feet, then the conversion factor would be 0.052, and my answer for pressure would be in PSI. So in the annulus between the tubing and the casing, I have 9 feet, 9 ppg fluid, and from the top to the bottom, from the top of the well to the packer, the pressure would be 3,042 psi. Now, if I have some angular pressure on the surface, this will add up on top of that surface annulus pressure. At this pressure, the force on the top of the packer is basically 3,042 times 14.81 square inches. What I'm basically doing here is pressure times cross-sectional area get stress, force. I get something like 45,052 pound force. The force at the bottom of the packer is the same in this case, but bigger cross-sectional area. So the pressure is the same, cross-sectional area is bigger. So pressure times the bigger cross-sectional area is equal to a bigger force. So that is 49,007 pound force. So you see, the small change in the cross-sectional area, 4,000 pounds force, which is quite a bit. So small area changes, big force changes at the same pressure. The difference, 49,007 minus 45,052 is about 3,955 pound force is buoyancy force. I'm pushing the piker upwards by this buoyancy force of 4,000 pounds, 4,000 pound force, which is quite a bit. Okay, now forcing it upwards, if I'm holding it in place and I'm forcing it upwards, what is the chance I'm gonna get the tubing? What is the chance of the problem I'm gonna get? I may get tubing backing or backing of the tubing in place. So this is something I need to worry about. So I need to deal with it. Generally, there are two ways you can deal with it. One of them is better than the other. We'll talk about it. It becomes clear. So, sample problem number 3. The well from example problem number 2 is acetized by pumping 6.9 ppg acid down the tubing with a packer set at 1,000 psi from the surface. This is surface pressure, 1,000 psi. So I have now fluid inside my annulus, my tubing that is different than outside, and I also have surface pressure. So I take this 0.052 times 6.9 times 6,500 feet. 6.9 is ppg, so the answer is 2,332 psi. And the pressure at the bottom of the tubing will be this value plus 1,000 from the surface. The annulus pressure remains 3,042 because the packer is set at that pressure. We calculated that from previous problem. So 3,042, and the pressure at the bottom is 3,332. So I have more pressure at the bottom pushing me up than from the top pushing down. The downward force on the packer is 7,000 plus 4,552, which is 52,050 pound force. That's the pressure at which I said the force at which I set it with, plus what I calculated. Sorry, pushing it down. Remember, I set it in tension. And the upward force is 3,332 times 16.11 square inches. That gives you something like 53,680 pound force. So force imbalance from between below and up. An imbalance by what? 1,630 pound force. So I'm pushing my packer upwards by 1,630 pound force. And the difference is that 3332 psi acting on 16.11 square inches to 3042 psi acting on 14.81 or something square inches. So I'm really pushing my packer upwards. That's what I'm trying to say. So, but the packer is set with a 7,000 feet downward force. It's still not enough. Okay, you set it with a 7,000 feet downward force, and we did take it into account earlier. So I'm not mentioning it here so that you need to do something. I'm saying you already took the effort to apply a downward force on the packer, a considerable downward force. It's not a little, okay? You set it in tension, and still you have a force pushing it upwards, okay? And this force is trying to backhaul your tubing. And this is what you're afraid of. So it will unseat or backhaul even. Might not backhaul, but still you will get problems with this amount of force. It's quite a bit. So what are you gonna do? One way to do it is to apply 8,630 pound force initially. Instead of applying 7,000, apply 8,630 at the beginning. This is not a good idea because when you are setting the packer at that tremendous stresses, you will probably cause problems, including buckling, actually, including buckling. A good idea, a better idea is to convert that change in the difference in the what you are missing in the pound force, convert it into PSI for a cross-sectional area of that the small one, the 14 point, what is on the top, and apply it on the surface from the casing side. So when you have pressure on the surface applied on the casing that pushes the packer down, okay? This pressure is like in the same direction at which you set the packer, at which you set the tubing, but it's basically pushing it down. So it adds up to the 7,000. It becomes basically 8,630, but it's from the casing side. So this is a much better idea. Okay, and then, yeah, 14.81 square inch times 583 PSI. Remember, PSI is pounds per square inch. You multiply by the inch square, the inches square and square inches cancel out, so you just have pound force. So ultimately, you are taking care of that problem. And what I'm trying to say here is that I have something like this. I have something like this, and then the tubing which has walls of its own. And we have a packer. The packer is at the bottom of the tubing. Also very important. And then you're asking me, okay, what if I already set the packer with 7,000 pound force, okay? What if I really needed 8,630, and I'm like, are you gonna put further? Okay, you may damage it, it may not be buckling that you're gonna cause, but you're gonna weaken it and it's easier to buckle. Or you come here on the surface and you say, okay, what fluid do I have between the casing and the tubing? I have this amount of fluid, 9 ppg, what we said in example problem number 2. I say, yes, but not enough. Apply 583 psi, excuse me, on that annulus. So now it's not just the weight of the fluid, of the light blue color fluid. It's the weight of the light blue color fluid plus the 583 from the surface. Excuse me, from the surface. So I end up balancing everything out. Okay, any questions? Uh, 1 second. We will be moving to something a little bit different as a subtopic. Before I close down about the Packers, I mean, I went by very fast. And yeah, I mean, it's a little bit beyond the charter of this course, but you need to have some good knowledge on how the Packers work, etc., etc. Pumping down wireline operations. So let me see if I have any urgent email. Nothing. Okay. The earth, is not transparent. It's opaque. You cannot see what goes on 10,000 feet beneath your feet. So you are guessing. Okay. Just like we did in drilling, we're like, we don't know where the kick is. In the simulator, you know exactly where the kick is, and then you wait it to appear. So you don't really know in real life where the kick is. You think you know, and you hope that you are not too wrong about where you think it is. Now, same thing in hydraulic fracturing operations, in workovers. When you have to pump something downhole, you really want to know how far you are or estimate. And there is a lot of corrections that need to be made. Sometimes you have some significant volume that is needed to fill the surface equipment. So before the fluid starts going downhole, you need to fill up a lot of tubulars on the surface. That is like from the blender that you mix your fracturing fluids, from those conduits that take you to the missile, as we call it, and then the frac tree, etc., etc. There is a lot of pipe on the surface. A lot of pipe on the surface. So wireline tool string is almost exclusively pumped down to depth to set plug and perforate with frac pumps. The process is called pump down for short. And you need to take into account like those volumes, basically. That's what I'm trying to say. Wireline pump down operations separate from frac by isolating well at zipper manifold. We are going to talk about those. Is basically zipper frac manifold. Zipper manifold is to stimulate multiple wells at the same time. So you go from one stage here to one stage for that well, the other well, and then one stage back to the first well, and so on and so forth. We are going to learn more about that on the third module. I know it's unclear now. It's just some things I want to introduce. It's going to become clear, though, I promise. General pumping down process, okay? After equalizing pressure within lubricator and wellhead with well pressure, the well is open. So you open the well at balanced conditions. Okay? You don't want the fluid to start moving when you basically open the ramps and get the well to flow. If there is pressure changes between the workover equipment and the lubricator and the wellhead, fluids will start moving. There will be a lot of motion. It can cause all sorts of trouble, break stuff, injure people, etc., etc. When you open the well, you want to do it very, very cautiously. By the way, the homework question, the last two questions of the homework was pump down problems, but we didn't include anything about the surface, slippage of the surface as they call it. Fluid used to occupy equipment on the surface. Sort of like we did in drilling with a hydraulic loop, just that. Wire line will then free fall to a depth near the liner top. Speeds will increase as the tool string progresses downhole due to increased line weight. Wireline engineers will then reduce speed to and note the line tension, then slowly fall through the liner's top around the heel. The heel is the side of the lateral well that is closer to you. So this is the process that they follow, which is not very important for us right now. Once the tool string is close to the heel of the lateral, engineers will call for pump down to slowly increase rate, usually call for 2-3 barrels per minute increases in rate until the rate limit, speed limit, and pressure limit is reached. Mark your pump joints or short joints. You have joints that are very short intentionally because they are used as markings. When you apply pressure and you hit a joint, you will hit a joint much faster than other joints because the distance between other joints is something like 30 feet. This one is like, 2 feet or something. This, even 1.5 feet. Many times a pump joint is colored red. Other times, I took this picture from a well. It was the first time I saw a yellow pump joint. So this was a well it was a drilling rig in West Texas. I think by Barstow. Oh, no. Between Barstow and Odessa, about that area. A marker pump joint is significantly shorter than other joints in the string so that it is easily noticeable on correlation logs when retrieving a work string. You know where you put the pump joint is used as a yardstick. Okay, this, if I wiggle the logs and I get a pressure increase every time I'm hitting a pump joint, when I hit it's gonna be like a break from the pattern. So it will be, or it will be distinguished. That's why it's for me that we're using pump joints. In the past, many years ago, last century, when they were drilling during the boom towns, they were drilling wildcats, and there was a lot of competition between people. They would pay kids to sit down near the rig and count how many how many joints or strands of pipe, drill pipe, are running into the well. And then a joint is 30 feet. A strand is 3 times that. If you add them all together, you will understand how deep the well is, especially back when everything was vertical. So you know how deep they went to heat oil. Your competitor, how deep they went to heat oil. In this case, you may use a marker joint, a pump joint, like every 1,000 feet, or like intentionally so that you can get a reference. And yeah, I mean, I don't think I'm gonna start perforating today because it's gonna take a long time and it's an important topic. But yeah, I will start the review. And like I said, for the exam, you only need to worry about the first 20 slides of module 2 and everything from module 1. So we really finish here, including the fishing tools, of course, and the first 2 homeworks. So let me open Blackboard. I need my credentials. Okay. So module 1. I made some more changes, but it was like very, very minimal, like grammar and stuff. I still have a lot of room for development of my material, but give me some mercy because when I came over here in 2023, I really didn't have any material. Like people have left, they didn't leave anything behind. So I had to start from scratch, which wasn't a bad idea when I actually saw the material that they were using. But I was making a lot of mistakes as I was going along, and then I had to fix them, etc., etc. But yeah, so this time they are much better. It's just there is still some small room for improvement here and there. So we started module 1 by basically talking about the importance of having a mechanical model for the air. We call it a mechanical earth model, actually, MEM. If you hear somebody, I have a 3D MEM mechanical earth model in 3 dimensions. For geomechanics people with relation to petroleum engineering, this is a model that relates stress and displacement. So I apply this kind of stress to the object, it's gonna get this kind of deformation. Deformation is a non-quantitative term. Displacement is more of a quantitative term, but strain is a dimensionless quantitative term. So what I really want is a model that will relate stress and strain. The easiest model that you can apply to a solid material is what you learn in solid mechanics, which is basically linear elasticity. Okay? It's a model that obeys Hooke's law in 3 dimensions for small deformations. And there is a lot of derivations going on, which I suppose you go through them in solid mechanics. and you go through them to some extent in the geomechanics. But ultimately, you end up with 6 elastic moduli. If you know these 6 moduli, you can describe how the model would behave, okay, or the model solid would behave. Now, the way these elastic moduli are connected to each other is so simple and linear that you just need to know 2 of them to get the other 4. So you need 6 to describe how the model behaves, but you really need 2 to get the other, to get everything else. So that's why when I say I have this rock, this reservoir, and I want to build a geomechanical model for this reservoir, and I'm going to ask you, okay, what are the geomechanical inputs? And you may say, Young modulus is this, Poisson's ratio is that. Okay, then I assume that you are using linear elasticity. So I take here I come here at the table, and I say, well, I come here at the table, and I go basically, okay, this would be my, this is how I would calculate my bulk modulus. This is how I would calculate my Lamé second parameter, my shear modulus, my Lamé first parameter, and then I have everything. But unfortunately, in real life, rocks don't behave very linearly. There is a lot of anisotropy involved, and actually heterogeneity. Anisotropy is change of the parameters with respect to direction, and the other heterogeneity is change with respect to region. So I move from this part of the reservoir to that part, I see different kind of positions. And then I look here, I see one value. I look here, I see another value. I look behind me, I see another value. You know, it's a degree of non-uniformities inside the reservoir. Now, let me erase. Where is it? Oh, there you go. Sorry. I moved the toolbar around and I couldn't find it. It was in front of me, but on the wrong side. I wasn't looking there. But anyway, this is what you need about that stuff, that portion of the class. And then we said, okay, rocks are unique in a different sense as well. They are soaked with fluid. They have fluid under high pressure. And fluid can move inside those pores, in and out of the pores, change the pressure of the fluid inside the pores, and make the pores bigger and smaller. This is what we call poroelastic deformation, which is very, very complicated to model mathematically. And we make some smaller terms for that. And most importantly, these are dynamic. They are temperature related. And when you see most of the equations that we see in class, they are not very dynamic. You rarely see time as an input in those equations. Now, when it comes to the subsurface stress stated, I'm talking about external conditions acting on my reservoir, let's say. The subsurface stress state can be characterized by 3 what we call in situ principal stresses. Those are mutually orthogonal. So they are at 90 degrees of each other and they are compressive. So the most compressive one gets assigned as 1, least compressive as 3, intermediate as 2. And if I want to account of the pore pressure, remember that pore pressure acts at every direction. So I just remove it, subtract it from each one. Okay, it acts against each of the in situ principal stresses. Now, well, frame of reference matters, and it does. The real stress state is not 3 values. The real stress state at a given condition, given situation, is actually a matrix of 9 values. It's called the stress tensor. Okay, 3 of those values are normal stresses, and 6 of those values are shear stresses. And the uniqueness of that is that for a stress state to be stable, to be actually stable, have no rotation, no motion, nothing, it needs to be diagonal and how do you say one side mirrors the other? Not reflective.
Orthogonal.
Symmetric. Shamel, what did you say?
I thought it's orthogonal.
Well, symmetric, which is similar to that. Orthogonal is they are at 90 degrees with each other. The stresses, that's what it says basically. So imagine I come here and I put a mirror like this. What I see here, I see here. So my S12 is equal to S21. My S23 is equal to S32. My S13 is equal to S31. Okay, always. Otherwise, I have an instability. It's possible that I have a temporarily unstable stress state. Okay. Can you think of a time when I have a temporarily unstable stress state? During an earthquake, when tectonic plates are moving, I have a temporarily unstable stress state. But for our stuff, and it's good for us mathematically, is that I'm going to expect these 3 qualities to be the case. So it's not likely I'm not saying that every stress tensor you are going to encounter in your life is diagonally symmetric, but I'm going to say that everyone, well, most of them will be. Otherwise, it's unlikely that you are drilling in a place at the same time that an earthquake takes place. You know? It just means that you are stable. That's what I'm trying to say. And the easiest way to deal with this complicated stress state is you cannot deal with the stress state itself. That's Mother Nature. Okay, you are just gonna deal with the way you are aligning your frame of reference. So if you set your axis a certain way, you can make all the shear stresses go to 0, and then you are only dealing with the normal stresses. By the way, something I don't know if I stressed it when I was going through the actual lecture on this, is that when you subtract pore pressure, you only subtract it from the normal stresses, not from the shear stresses. That's one thing. But if you see the second picture here at the bottom right, I just played with my frame of reference. I tilted it a certain way so that it made all the shear stresses become 0. And then what I had in my normal position was what we call the principal stresses. Okay, that's when there is no shear stresses. And something to stress before I have to go, I guess this class will be over. I have to just make sure a common mistake that students do is this is not the same as this. Okay, I take this and I start moving it around, and I I get to a point where everything else becomes zero. And then I have the principal stresses. And this is what you did mathematically. No, you didn't do it in this class. I believe you did it in geomechanics when you have to algebraically, well, you have to find the eigenvalues of the tensor. These are the principal stresses, and then the eigenvectors are the direction of the stresses. And I think we had an exercise on that. Okay. And I believe I have to go because the students of the next class are going to show up. We'll carry with our review next time. Please bring any questions that you may have. Also, please bring, well, the homework would be due on Thursday, 1 minute before midnight. And if you have any questions, you can also bring them to me during the lecture on Thursday. Tomorrow's office hours will have to be cut short. Tomorrow is a crazy day for me. I have a meeting from 12 to 1, and then another one from 1 to 2. So my office hours tomorrow will be only from 12 to 1. But I am available, and the TA is also available. If you want us, we can arrange for a separate Zoom call or anything you want to help you with the homework. I'm not going to give you the answers, but yeah. So yeah. Yeah, I will be, and then we finish the review next lecture, and then the exam is going to be on Tuesday. Thank you very much. Have a nice rest of your day. Donald, I did receive your email.
Thank you, Professor.
Thank you, Shamel. Thank you. Donald, I did receive your email. I just didn't respond yet.
You think it's good?
I think it makes sense. It's just you need to narrow down.
Yeah, I'll try to narrow it down more. Yeah.
Say that again?
I'll try to narrow it down more. Yeah.
Yeah. If you narrowed it down to the specific hypothesis, you are going to be gold.
All right, thank you.
I mean, we're close. It's not, but it's a good idea for sure.
Yeah.
And
Right,
it
thank
can
you.
be made to work, you know?
Yeah.
Anyway, I'll see you.
All right, see ya.